All right, so this is graphics in the media, and because there are so many different ways to display data, we're basically just going to go over a few common ones that you'll see displayed by popular media and how to interpret those. All right, so now we're kind of going beyond basic graphs. So we talked about just basic histograms, basic bar charts, pie charts, but there are a few that are sort of beyond that. A multiple bar graph has two or more sets of bars that allow comparison between two or more data sets. All data has to have the same category so that they can be displayed on the same graph. So like the one on my lead slide, this is a multiple bar graph. And this is percent of Americans ranking among the 3 most important media services they subscribe to. So this one's actually pretty complex. So the categories are pay TV, video streaming, music streaming, newspaper, print, or digital. But then they've basically color-coded these by age groups, so age demographic. So 92% of 68 and over year olds think that pay TV is the most important media service that they subscribe to. So that's called a multiple bar graph. In cases for which data categories are quantitative instead of categorical, we would use a multiple line chart. And then a stack plot is the worst graph on the planet. And I don't understand why it's in use. I'll show you what it looks like and why I have such a disgust for it. All right, so here's a multiple bar graph of median annual earnings of full-time workers ages 25 and up. And it's by, the categories are education level, right? And the multiple data sets are divided between men and women. All right, what's one big takeaway from this? Give me one key characteristic that you can take from this data set being divided by gender. Men what? What was it? Yeah, at every level. Another key takeaway is that the pattern is the same in both. As we increase education level, the median pay raise goes up for each, right? But at every education level, as of when this data set was collected, which I think was in 2012, men made more than women. Yeah, it's kind of gross. I'm a hero. My wife makes more than me, so don't worry about us. We're progressive. She crushes me. All right, here's an example of a multiple line chart. So here we're looking at the x-axis being time and the unemployment rate by categories of education level. So the key takeaway here, right, you can see that they all tend to fluctuate the same way. Although the unemployment rate for somebody with a bachelor's degree or higher is always lower than the lower education levels, right? Meaning higher unemployment for people who have some college education, higher unemployment rate for those who only have a high school diploma, and then the highest will be the group of people who are not a high school graduate. They regularly have the highest unemployment rate, although all the patterns seem to trend in the same way. Does that make sense? All right, and this is just verbalizing what we went over in those last two graphs. So the first one was people with greater education have significantly higher median incomes, and for equivalent levels of educational attainment, women still earn much less than men. And no matter what the unemployment rate, unemployment has always been significantly lower for more highly educated people. This is a stack plot. I don't like it. So the whole thing about visualizing data is you're supposed to get to a point where you can intuitively understand what's going on in the data set, right? We're not robots. I can't just give you a matrix of numbers and you're like, oh, I get it. I can see the patterns here. That's why we have visual displays. Generally, yeah, so this is exactly. I don't think the idea in a stack plot with multiple data sets like this is you want to be able to compare between the groups. So this is average estimated undergraduate budgets, and it's broken up into categories of like things you would pay for at school, right? Tuition and fees, room and board, other expenses, books and supplies, and transportation. Now, what they've done is created a data set for each type of school. We got your basically community college, right? That's a 2-year, called a public 2-year community college. Your state schools, your out-of-state schools, and your private, your Notre Dames, basically, right? The reason I hate the stack plot is it's only really useful in the first category. Like, I can clearly see in the dark blue, I can clearly compare between the groups' tuition and fees. And I can see that it's most expensive at private schools and it's cheapest at community colleges, right? But then every category after that, it becomes difficult to compare. And what they end up doing is having just to write out the data anyway. So what's the point of the visual? Because if I didn't have those numbers there, it would be extremely difficult for me just by shape and size to be able to compare between these two or these two because they're off-centered. You know what I mean? Anyway, I think that they're popular in media mostly because they're compact and they can fit on a single page, right? But I don't think they do much in terms of visualizing the data for you. I think they're kind of trash. Speaking of trash, I also don't like these wedge plots. Yeah, and it's a difficult one to visualize because, so this is the death rate for cardiovascular diseases, for serious diseases rather, from 1900 to 2011. So my x-axis is time. My y-axis is the death rate per 100,000. But for example, if I wanted to find the death rate for cardiovascular disease in 1980, what that corresponds to is this vertical distance between, so I would go to 1980 and I would need to measure what this vertical distance is, which is 620 minus 180. What is that? 440. So the death rate corresponds to the vertical distance on that wedge over time. I guess these aren't as bad because they do give you a visualization. Like when the wedge starts getting smaller, you can tell that that death rate is shrinking, right? So like, look at tuberculosis. You can kind of visually tell. It used to be a big deal in 1900, right? And then over time, it became less and less of a big deal until 1950. Very small death rate, right? And the reason is now we have, like, we can be immunized against tuberculosis, so that's why it's pretty much gone completely away. What has pneumonia done over time? Mostly shrunk, right? But the thing I think is difficult about reading these is like the death, let's look at pneumonia's death rate in 1980. That little piece, that vertical distance corresponds to the death rate, right? The pneumonia death rate in maybe 1999 is about the same because these vertical heights are about the same, right? So the thing that I tend to find difficult about this is it's on a downslope, but that has nothing to do with the death rate itself. The death rate corresponds to this vertical height, which is the same basically from here to here, right? The only reason it's going down is because it's on top of the cardiovascular death rate, which is shrinking over time. This is getting smaller. Cancer is increasing over time, right? What do you think the reasoning behind that is? Because I would imagine we've developed much better healthcare for cancer since the year 1900. Would you agree with that? Why do you think the death rate due to cancer is that wedge seems to be growing, doesn't it? Any ideas? That could be it. There could have been some probably better health recording as time went on. But what's going on with lifespan from 1900 till now? It's increased quite a bit, right? You have a larger population, so that we have an increasing population, and we're not looking at percent here, so we are looking at raw numbers per 100,000. But as you increase lifespan, the probability of getting cancer also increases, basically. If you live long enough, you will get cancer. That sounds depressing, but that's what happens. As the longer you live, the more likely you are to develop some form of cancer. And as people have lived longer and lifespan continues to increase, more cancers have developed or become more common. All right. So yeah, we're going to talk about some geographical data sets, and we'll take a look at what I think Dylan brought it up, what's called a topographical map. These are really intuitive. I'm sure you've seen this. This is just a color-coded geographical data set where it's oil use by state per person in gallons of oil equivalent. All right, so what information could we get here? There seems to be high oil use up here. Why might that be? What do we use oil to do? Energy? What do these states have in common? They're cold, right? So they probably use more oil because they have to use more energy to heat. Versus Arizona, one of the lowest per person in terms of oil. All right, a contour map. This might be new to you. So this is a contour map of temperature or of average temperatures for these these regions. And it just says widely separated contours mean large regions have nearly the same temperature. So like all of this region in this color between contours have roughly the same average temperatures. Whereas closely packed contours means a large temperature distance over a short distance. So if you were to drive from like Ohio, southern Ohio up to Minnesota, you would go through 4 different average temperature zones, right? So it's pretty intuitive. Okay, so let's talk about 3-dimensional graphics. The thing about plotting graphs is there's mathematics behind it. So like there's a really interesting video I'll try and find that's about map making. And the map that you guys, you know that the map that of the US that you guys are used to looking at. I'm thinking of like the old school style pull down ones that teachers used to have in their room. That's called the Mercator projection. And the deal is the globe is three-dimensional, right? It's roughly a sphere. You can't take something three-dimensional and lay it flat without getting some sort of distortion. So the Mercator projection keeps distance true. So the distances between places are truly what they are on the globe, but then it sacrifices size. It distorts some size. So like, for example, Alaska is huge on the Mercator projection, and Africa is super small. And so I want to find the video. It's an interesting article. It's like a Vox video about the impact the Mercator projection has had on the African community and the African American community because it's minimized those countries so much. And it may sound like a reach, but there's some very like interesting points that they talk about in this video, if I can find it. But the same goes with three-dimensional graphics. They're not really three-dimensional. They're on a flat surface. They're on your screen or they're on a piece of paper, right? So there's going to be visual distortion because, again, just like you can't take a globe and lay it flat without distortion, you can't have three dimensions on a two-dimensional surface. There's always some distortion. So we want to be really careful with three-dimensional graphics, although it does allow us to graph more data sets in one space. But here you go. So here's an example of a 3D graphic. It's CO2 emissions by year and by country, right? So based on this figure, when did China surpass Russia in total carbon dioxide emissions? So China's in yellow, Russia's in red, and it looks like that happened here, right? And so in the year, yeah, so it happened there. So they're saying between 1990 and 1995. Am I looking? Oh, I'm looking at the wrong ones. That's the US and China. Sorry about that. I was like, what? All right, so sorry. China and Russia. China's in yellow. Russia's in light blue. Okay. So, yeah. China was behind Russia here. Then they're in front of Russia here. So between 1990 and 1995. Let me see what you sent me, Trey. Don't rickroll me. Is that what you did?
No.
Okay. So this is the true size of, and then what do you do?
Close up that box, and then you can drag the cupcake, and like where's the equator to the right side, and then you'll put it up. Like this, so it's like from the figure.
Ah. So like US.
The yellow one, that's like the figure.
Wait, I don't understand what's going on.
Go further north, you'll see how
Oh, okay. Right. Okay, so you can see that like Greenland looks really big on this Mercator projection, but if you drag the US over it, the US is really much bigger than Greenland. But the visual on this projection makes Greenland look super, super large. All right, I got it. Yeah, that's cool. Okay, few cautions that I was just talking about graphs. Perceptual distortions. Many graphics are drawn in a way that distorts our perception of them. One of my least favorites is when we have like a like 3D pie charts where they try and make it look like it's like an actual physical cylinder, and they'll kind of draw it out like this. But because it's in 2 dimensions, that's going to distort the wedges that are furthest away and make them look much smaller. So if you're ever using a pie chart, just do a normal pie chart. Don't do a fancy 3D pie chart because it does provide visual distortion. Make sure you pay attention to the scales. So some tricks that can happen is they could be on a logarithmic scale instead of on just a linear scale, and that'll distort the way the graph looks. And then pictographs. These are dumb and bad. Pictographs are when we use pictures instead of bars and bar graphs, and you stack up pictures, but they can cause lots of visual distortion, right? Like here's a perceptual distortion one. Your eye is drawn to the area of that dollar, but what they're doing is having the length of the dollar represent the the worth. So this is like a graph that's supposed to be showing inflation, right? If we take 1980 to be the value of a dollar is $1, then here's how it's changed over time. In 1990, the value of that same dollar was only 63 cents, and in 2005 it was only 42 cents. Well, what they are doing is they're actually using just the horizontal distance to represent the proportion, but they've drawn a picture where your eye is drawn to the area. And actually, this area is much smaller than a 6% reduction from the original, okay? Women as a percentage of all college students. In this one, they start the scale at 30, and over time, it looks like it's increased rapidly, right? But that's because they start the scale at 30. If we actually start the scale at 0, it's a much less drastic situation over time, right? So you'll see companies do this when they're trying to make it look like there was a large amount of change over time. They'll distort the scale, not start it at 0. All right, and then this is our world scale, our world population in billions of people. And the problem with this is, hey, it just looks like we've been increasing kind of linearly over time, right? But in fact, when you look at the time gaps, this is like 123 years. This is only 40 or 33 years. This is then 14 years. The scales, the gaps between time are decreasing, right? Which means actually what we have here is exponential growth over time, and it's just made to look linear because there's not the same time gap between each year. All right, that's it. So pretty short problem set today. Remember that